It's my great pleasure to introduce Jeremy Avigad from Carnegie Mellon University, my dear colleague. Come on, Egbert, have a seat. Jeremy's going to tell us about the Lean Theorem Prover, which is a very exciting program that's headquartered at CMU and other places. We have a very active research group there on Lean, and I think it's a promising new proof assistant. Thanks, Jeremy.
So you'll notice I changed the title a little bit. The thought originally was that later in the program we will give some kind of tutorial introduction to Lean. So I thought today I would just give you a quick overview of Lean and then talk about one particular aspect, namely metaprogramming in Lean. But in preparing the slides, I realized that there's just a whole lot that I want to tell you about Lean in general. So this is really more of an introductory survey, though at the end I will spend, if things go well, I'll spend a good chunk of time talking about metaprogramming. So Lean is a new interactive theorem prover. As I'll indicate later on, there are a lot of people working on it and contributing to it, but the driving force and font of energy is Leo Demora at Microsoft Research. The project is an open source project, so all the source is available right now on GitHub, and it's released under a very permissive license. So Apache 2.0 means pretty much you can do whatever you want with it. You can build things and you can sell it if you want to. And the idea behind that was really to make it a community resource, a community project, so that people can contribute to it, knowing that they're contributing to the common good. When you look around today, I mean, there are a number of interactive theorem provers out there. So I've listed some of them. In keeping with the theme of the program, tried to focus on ones that have substantial mathematical libraries. But again, I don't mean to consult anybody, but I've left some off. If I left your favorite theorem prover off.
Well, you did, actually.
That's why I said some. Oh, I said some systems. Okay, some systems. But so a natural question is why develop yet another one? Even if you look at these, even the youngest among these have been around for quite a while. I mean, I don't know which are the youngest, but I mean, for example, Cook and Isabel, which are widely used, have been around since the 80s, and that's already 30 years. And so we've learned a lot about interactive theorem proving since then. And so it's nice to be able to have sort of a fresh start and try to sort of take what we've learned and build a new theorem prover that incorporates all the best understanding. So in particular, we've stolen ideas from a number of existing theorem provers, including Avigad, especially Avigad. We've stolen a lot from that as well. And Frank Friedrich once said to me that the problem with studying and working with different theorem provers is that you end up hating all of them. Right? Because what happens is each one has features that you really like, but then you go to another one and whatever features you have, you're always really ticked off about the ones that that the other one has that you don't have. But we can then sort of look around and try to sort of take the best features from a number of different theorem provers and bring them together. And so that really characterizes the project. We're not trying to break radically new theoretical ground or do something experimental. Rather, we're trying to develop a mature theorem prover, a very practical theorem prover that incorporates the best understanding we have today. That's not to say that there's no insight and novelty. I mean, in sort of in dealing with design constraints and designing a workable system, you come across problems, you have to craft novel solutions. But the emphasis, again, is on developing a theorem prover that works in practice, a very practical one, rather than breaking new theoretical ground. One of the goals behind the project is to bring interactive theorem proving and automated reasoning together. So, from my perspective, I spent far more time than I ever thought I would formalizing mathematics interactively, and I do think that it's in order to bring interactive theorem proving into the mainstream, make it sort of a very widely usable tool and method. We'll need better automation. We'll need better automated support. Leo came from the other direction. So Leo is an automation guy. He's the developer of Z3, or as you Brits would say, Z3, which is widely used in software verification projects. And his motivation was largely to respond to things that he felt were shortcomings of that type of approach. In particular, he's frustrated by the fact that all these theorem provers use lots of optimizations and lots of tricks and do lots of complicated things, and it's really easy to make mistakes. I mean, so he was concerned that you really want to have some kind of formal guarantees that your theorem prover is doing what you think it is. Also, I mean, Z3 is first order, very, very close to quantifier free. They always regretted the fact that lambda expressions weren't built in from scratch. So you're always feeling limitations of language. So you really want to have a broad expressive language. Also, Z3 people, even though it's an automated tool, I mean, you send it a source file and it runs it and either finds a solution to the constraints you give it, or shows it knows, or declares that no such solution is possible. People would nonetheless use it interactively. I mean, they would send it a source file, they would run it, they would get a response, they would tinker, do it again. And so, Leo thought that it would be good to have automation that you could use, a system use interactively. So you can think of it, instead of an interactive theorem prover, think of it as sort of the next version of Z3. It's a version of Z3 that has, it's proof producing and has a more expressive language and can be used interactively and so on. And as will become clear later in the talk, we're also now thinking of Lean as a programming language. And not just a programming language, but a real rich programming environment. In particular, it's a programming environment in which the programs you write come with a precise formal semantics, so you can reason about them formally and precisely. And this is the real exciting part. You can also use this programming language to extend the capabilities of the system itself. So that's something that I'll be talking about towards the end. So the goals are, to verify mathematics, verify hardware and software and hybrid systems, and so on. Also, I'm hoping the system, in the long run, we'll be able to use it not just to verify theorems that we know damn well are true, but to explore mathematics and actually, it'll be a tool to help us in discovery as well. We want to use it for education, but again, the main goal is really just to come up with a system that will bring formal methods to analysis that's easy and convenient to use. A little bit of history. The project began in 2013. First version, Lean 1, was short-lived, but Lean 2 was sort of announced to the world in some conferences in 2015. Lean 2 is, was and still is a very good system, I think, but there were enough. Leo is a perfectionist and had enough frustration with some of the fundamental choices that were made that he really undertook almost a total rewrite of the system last year. And the new version, Lean 3, is now in place, so that's what we're using now. And we still have a long way to go, but today my goal is to give you a sense of what's there. Let me mention that Lean 2 has special support for homotopy type theory, and that support is not yet in Lean 3. So for now, homotopy type theory. So Lean 2 has a very extensive homotopy type theory library, and you'll have opportunities, I think, to learn about later in the program. So I should mention that that's there. Okay, but today I'm going to focus on Lean 3. Here are some people associated with it. Again, as will become clear soon, it's the distinction between code base and libraries is starting to blur because now you can extend functionality of Lean sort of in Lean itself. But if you think of code base as really being the C++ code, note that it's a really small group. There aren't a lot of people working on it. It's really Leo, and the rest are all PhD students. But then a number of us working in various aspects of the system and developing the library. So a lot of people here are at Carnegie Mellon or were or came through Carnegie Mellon at some point, and a lot of people have contributed. This isn't a complete list. Lots of people have contributed either substantial code or library or advice and ideas. Okay, so let me give you a quick rundown of the things, notable features of Lean, and a lot of them I'll be expanding on soon. So I'll just run through them quickly and then say more about most of them later. So the system is based on a version of the calculus of inductive constructions. I'll give you the precise details in a minute. It's written in C++ for performance. It'll do multitasking. It's very efficient. It uses your cores very intelligently and wisely. There's a small trusted kernel. So for dependent type theory, especially, it's remarkably small. And there are at least 2 independent type checkers. That will that can check results independently. It supports constructive reasoning, but also semi-constructive and classical versions. There's nice syntax, a powerful elaborator, type class inference is well integrated into the elaborator. I'll tell you about the function definition system that gives you nice ways of defining functions and compiling them down to primitives. You can write proofs in a declarative style, a tactic style proof, you can interleave them. There's really good support for editors. So you can run Lean in a server mode and use an editor up front. And so it'll give you, continuous proof checking and feedback, while you're working with the system. And so right now there are modes for Emacs and VS Code they're actively used. But again, it's pick your favorite editor, and you can invest some time and use Lean as a backend. There's also Lean also compiles down to JavaScript, and so you can actually run it in your browser without installing anything. And there's a performance about an order of magnitude slower than the native one, but that's still very good for tutorials and teaching and so on. Later I'll talk about the fastbytecode interpreter, so you can sort of evaluate definitions quickly. So that's what makes it into a programming language. There's a framework for metaprogramming. I'll tell you about that. The profiler, you can a very customizable debugger. You can basically write your own debugger. There are hooks for that. Automation is starting to come to life. The simplifier. There's SMT-like gadgets. Well, I guess the most important thing, from my point of view, is that there are a lot of enthusiastic, talented young people, so I can include myself, young people. It's a fun project to be involved with because there are a lot of really bright, energetic people doing interesting things, and so it's just fun to see it happen. Okay, so let me tell you about the foundation. So in the last few days, we've seen a lot of axioms. They keep coming back. So I'm going to tell you what the system is. So here's a quick summary, but I'll expand on it. So the core, when you say calculus of inductive constructions, I know there are lots of versions, it's not really clear what you mean, so I'm not here to try to spell it out. So there's a hierarchy of universes, they're non-cumulative, and the bottom one is the type of propositions, so that's proof irrelevant and impredicative. There's a hierarchy of type universes, you have dependent function types and inductive types, so that's the core calculus of inductive constructions. On top of that, you can declare whatever axioms you want, but in the standard library, on top of that, we add a quotient construction with a computational rule and propositional extensionality. And the idea is that these things I'm calling them semi-constructive because they're still compatible with a worldview where everything is computable, with the understanding that, when you want to evaluate something, you basically erase all the propositional information, erase types, and you just evaluate. And the thing that breaks that is there's this one classical axiom, which is a choice axiom, which I'll tell you in a minute. So when you throw that in, you're no longer computable. But you can use all of these things, and Lean knows what is computable and what isn't.
And you have uniqueness of identity proofs.
We have more than that. We have any two proofs, inhabitants of the same proposition are definitionally equal. So strong proof of relevance. So the universes, internally are labeled sort 0, sort 1, sort 2, sort 3, and so on. But prop is just syntax for sort 0, and then type n is syntax for sort n plus 1. But you should think of the types as sort of increasingly large universes of data types, and prop is your type of assertions. And so prop is impredicative. You can quantify over big things and still end up with a proposition, and it's definitionally proof irrelevant. What I just said. So you want to think of, there it is. If you have a proposition P, and then two proofs of the proposition, then the system treats those things as not having any data at all. They're just tags, they're just markers, they're just witnesses or evidence that the proposition is true. You have dependent function types as usual, so pi, x, and a, beta of x is the type of functions that maps an element x in alpha to the type beta of x, and the usual beta reduction rule. We also have eta equivalents for functions, so definitionally those are recognized as being the same by the system. And also people usually don't put let definitions, they don't usually count it as part of logical foundations. Maybe they should, but anyway, we don't have let definitions in the system. And then as far as inductive types, it's actually inductive families following the recipe by Peter Dubier. Okay, so it's just the plain basic inductive families with constructors and the primitive recursive eliminators. So for example, when you declare the inductive type of vectors, so it's a family indexed by the natural numbers, so nil is a vector of length 0, and cons, takes a vector of length n and adds an element and gives you a vector of length n plus 1. And with that declaration, these are the 4 things you get. You get the data type, vector, you get the nil, the cons constructor, and you get the recursor. And the recursor says that if you want to define a function for vectors to something else, you basically give the value at 0, you give the value at nil, and you give the value on a cons, based on the value of the recursive call. Okay, and that's it. You don't get you don't get anything more than that. There's the computational rule for the recursor, and nothing more system. Okay. So that's the core, the pure fragment, the core calculus of inductive constructions. To that we add quotient types.
Can I interrupt just with a quick
Yes.
remark? For people who are interested in hot, you mentioned that in Lean 2 there's a hot branch, and that the foundations there are slightly different. I just want
Yes.
to mention so that people don't think we're cheating when we say
Yes.
we use Lean for hot. There it is proof relevant,
Yes.
and you don't have the prop at the bottom.
So
there's
here I'm
just
focusing
modifications.
exclusively on Lean 3, and so Lean 2 does have a separate kernel mode that is appropriate for.
And while we're asking questions, so in the core you don't have fancy sort of inductive recursive things. or
I'll spend a lot of
inductive
time on that. We do not have any of that. So that's all we compile. And I'll give you examples in just a moment. But anyhow, so on top of that, if you want quotients, we add quotients. And these 5, so I checked, so these are actually exactly equivalent to yours. And we have the computation rule that you would expect for quotients. So let me not, in the interest of time, because I have a lot to tell you, let me not.
Was there any reason why that doesn't make it into the core, as it were?
Oh, well, it is in the core in the sense that the computation rule is, it is built in.
Oh, I see.
We just, I don't know, this is really more just kind of stratifying the organization of
Oh, I see.
you can choose to use this or not if you're a real purist. But it is, it is.
So it computes definitionally.
It does compute definitionally. Yeah.
But when you write axioms,
So you can declare whatever axioms you want. What I'm just describing are the axioms that.
so when you say compute, the axiom or constant?
So
compute-
quotients are handled specially, that there is a kernel extension to handle the computational rules. So in general, you can just declare axioms.
But all that's constant and special computational.
But so there's special treatment. I guess what it is it's the lifting in the make. Yeah, and that's built in. That's a kernel.
I mean, we do know, of course, that you lose canonicity, as it were.
You do, right? So
Okay.
again, that's why I've separated away. If you're a purist.
I don't mind losing it, frankly.
Propositional extensionality, you can use if you want. And then finally, if you want to go classical, you just add choice. And actually, the choice principle we add, it's a remarkably simple statement. It's just that if alpha is not empty, then you can have an element of alpha. So on top of the other things, that's all you need. I mean, the idea is the reason. So as I said, the reason that propositional extensionality and quotients, are computationally, sort of acceptable is that the idea is when you evaluate, you just ignore all that stuff. But choice says you can't, right? That if you have, so the choice principle, non-empty alpha is equivalent to saying that if there is an X in alpha, such that true, then alpha. So it's a proposition. And so this really kind of just breaks, I mean, if you're thinking of propositions of things that have no data, this would sort of break that whole computational interpretation. So it's choice that really, makes you classical. And once you add choice, remarkably, you get the law of the excluded middle. I should mention function extensionality follows from the existence of quotients. That's not obvious, but it's true. So once we have quotients, we have function extensionality, propositional extensionality. Once you get choice, you have the excluded middle. And so here, once you've added choice, you really have a fully classical environment. Yeah.
What is U in sort U?
Oh, sorry. So there's a hierarchy of sorts, and they're polymorphic. So this is.
So U is a natural number?
So U is it's just so it's a variable ranging over. It's polymorphically, but you can instantiate them. You can have sort 1, sort 0, sort 1, sort 2.
can I index with something different from natural number?
Well, it's not really a natural number.
What's type?
It's a built-in
Is there a
thing.
sort?
So there's a sort zero. There's, you have, I mean, there are operations on sort. We can talk about the calculus of levels, but it is, we do make more explicit what's implicit in calc. So you can, yeah. But just think of that as just polymorphically ranging over the whole hierarchy of sorts. Yeah. Mostly the U gets instantiated by the elaborator automatically when you apply. There's, yeah.
So I can't abstract over U and form the function.
You can,
that sends
no,
you
no,
to
no, no,
sort
so
of
it's
U,
a
unfortunately.
sort of
Has there been any attempt of doing lean in lean somehow?
there is talk of that, yeah, so this is something that we would like.
That would be very fat.
Yeah. That's a
What's the existential? Is it a inductive type or is it?
I'm sorry, what is what?
The existential, is it an inductive type?
Yeah,
or-
so on the print, we use the inductive types to define the logical connectives, basic types, the existential quantifier. Yeah, so all of those are instances of inductive types. And the difference between, exists and sigmas, that exists lands in prop, and sigma lands in type. And so Lean keeps track of, it knows what things have used choice in a way that will block computation, and so it makes you, mark them as non-computable, or declare at the top of the file that everything you do is non-computable, or just don't bother me. But it knows independently, whether or not you tell it. If you mark something, if you don't mark it as non-computable, Lean will come back and say, you have to mark this as non-computable. If you mark something as non-computable, that is computable, it'll also tell you. So it knows. And the idea is anything that's computable, bytecode is generated right away. So it really is. I mean, it's not just computable in theory, but in practice.
Is there any particular reason for jumping straight to choice and not also including law of excluded middle as a kind of?
Oh, it's kind of. Oh, I guess you mean if you want to be.
If you want to have class
we
laws
just
without
we
choice.
just thought it was nice to just keep the axiomatic foundation just down to a minimum. So we got it down to sort of this. So even function extensionality we derive from the quotients. But again, if you wanted to just declare the excluded middle and use that and not use choice, you could.
I mean, these axioms are in some sort of prelude, are they? I mean, I could not use them if I didn't want to.
Yeah, they are declared. They are loaded. You can just not use them. You can also ask any theorem. You can ask me to tell you which axioms have been used. So I don't think there's a way to, other than just tying your hands and saying you can't. I mean, so they're always there for you to use, but you don't have to use them. Okay. And so so the primitive recursors that Leans give you are a very, very basic form of computation, not very flexible, hard to work with. And so the idea is to have more flexible means of defining functions. You want to have a way of defining functions in natural ways and compiling down to primitives. And so Leo's called that an equation compiler because you give it a bunch of equations and it compiles the function. So for example, you can write this definition, list addition, and it's kind of pattern matching. You give the cases, if you want to add two, so this is adding lists of any type that has an addition associated with it. And if you want to add the empty list to something or something to the empty list, you just return the empty list. And otherwise, you have the cons case. And Lean, keeps track of, make sure that all your cases are covered. If you leave out one, it'll give you a message that there are cases that you haven't covered. What was I gonna say? Yeah, but it compiles this down to primitive recursors. And this is a bytecode evaluator. You can just evaluate it in the file, and you get the little in your editor, your little squiggly thing. You put your cursor on there, and you can see the result of evaluating it.
Just talk me through the first line of def. So you're defining list add.
Oh yeah, so it's
curly brackets,
so alpha you declare as an implicit argument.
So
Yeah, and also the in addition, you're going to use it. You're going to apply it to apply it. You need a type that has a type class. So this is a type class declaration. You don't have to give it a name. It's sort of an anonymous argument, but that's the type class. So it's a special kind of implicit argument that we left anonymous. But you're defining a function from list alpha to list alpha to list alpha. And the clauses give the definition.
dependent pattern matching?
Yeah, so good, yeah. So first of all, yeah, it'll do structural recursion, so it'll do, I mean, that works, so that's the Fibonacci. And here, the compilation strategy, I mean, this is sort of the inefficient functional definition, but in fact, it compiles this down to a course of values recursion. So happily, this case actually does evaluate efficiently, so you can do that, and the result is instantaneous. I should mention, I'll come back, I'll talk about the virtual machine later, but natural numbers and integers are handled natively by the virtual machine, so that gives you a little more efficiency. But here's vector addition, and so defining, adding two vectors. So you give, if you want to add nil and nil, you get nil, and here's the cons case. And so, yeah, so it's dependent. This is a dependent elimination. Also, there are two cases, like there's the nil cons and the cons nil that are not listed. Lean, can detect from the fact that, can detect from the typing constraints that those two cases are impossible, and it fills in the plumbing to handle that. So it really does, it's really a fairly elaborate and complicated.
So I want to ask you what sounds like a silly question, but how did you type that? Literally at the keyboard.
Literally at the keyboard, yeah.
So did you have to type that and then it checked it, or did it help you find those dot underscores? Because that's the thing, right? I mean, dependent pattern matching is pretty subtle. If you had to write it all straight off yourself,
yeah.
It would
So
be
for the most part,
miserable,
we're
right?
writing it ourselves and getting our messages and then using them to fix it and so on.
So you don't have a sort of case split kind of thing.
We don't have like an actor like the expand.
You could.
We could, and actually,
really good.
work
You
just
should.
started on. So there's David Christensen, who's one of the Idris programmers, just spent a week at Microsoft and started implementing that kind of whole.
So that'd be really very useful.
So I mean, a lot is still happening. So yeah, so that I think is likely to happen soon. One thing that's going on here is when you when we implemented. Well, when Leo implemented the equation compiler, one thing that became clear is that the underscore, at least in Agda, is used in different ways. The underscore is kind of mysterious, right? Sometimes it's a wildcard pattern, and sometimes it's filled in implicitly. And so to get the equation compiler to work, that's what's happening here. This underscore is a wildcard. So in this case, the general patterns are, the general variables are A, B, W, and the N there, which you don't have to give a name. And everything else is not something that participates in the case matching and so on. They're just meant to be inferred implicitly. And so it takes a little bit of getting used to figure out where you have to put the dot underscores and so on. But it does, in some sense, clarify what patterns are being matched and what is really not part of the pattern matching, but just something that's being inferred. Also, nested and mutual inductive types are not part of the kernel. Again, the kernel is really very minimal. And so, for example, mutual inductive types, like defining even and odd simultaneously, that's compiled down to just to a plain vanilla inductive definition with indices, so an inductive family where you just have a Boolean that tells you whether you're doing the even or the odd part, which is remarkable. Also, these kind of nested definitions are not built into the kernel, right? You can't, use list, the list. So this uses the list definition. So when you declare this in Lean, what Lean does is actually looks up the definition of list, defines a mutual inductive type with tree and list tree at the same time, builds the isomorphism from list tree to list tree, and gives you the result. Okay, so it really does a lot of work to compile it down to.
That might have a big implication about how your pattern matching is going to work and whether it's really going to be effective or not.
Yes, so you do lose some computation. So not all the principles that you would get computational in Lean, Calc, or Agda. So you lose some computation, and as a result, some definitions will end up using well-founded recursion instead of what you would think of as being some kind of complicated structural recursion. So let me come to that in a minute. So let's see. So so here's an example of kind of a nested inductive definition. So here you're saying a term is either a constant, with some string name, or you're applying some string to a list of terms and getting another term. And then if you wanted to find something that calculates the number of constants, well, one way to do it, and again, the equation compiler is still being developed, but here's one way to do it. This does compile now. You define, the num constants, something that computes the number of constants and the number of constants in a list simultaneously. So you can define that by mutual recursion, and it works. You can just evaluate it. Okay. You can also do well-founded recursion. Again, it's sort of hot off the press. It's still in development. It's still got some rough edges. But so, for example, you can define natural number division. So to divide x by y, well, if y is strictly positive but less than or equal to x, then you want to take div x minus y, y plus 1. So that's the recursive call. But for the recursive call to make sense, you need to know that x minus y is strictly less than x. You need to know that you're decreasing in the first argument. And so you can just kind of stick that into the definition. And the equation compiler detects that it's not a structural recursion. It tries well-founded recursion. It knows that you have a well-founded ordering on the natural numbers, but less than is that. And it sort of looks for the constraints, and if it has that, it will find it and use it. And so here's this Ackermann's function that goes through. Here's just another example that I play with, just defining a natural number binary representation, sort of a list of zeros and ones. And so in the n+2 case, you recursively, you divide by 2 and convert that to a binary number, and then add either a 0 or 1 at the end. And again, to justify that, you need to show that n+2 over 2 is less than n+2.
And just be clear, the sorry wouldn't be in the actual.
Yeah, no, you would
It's just
actually
keep the
you would
slide,
actually either put it in there or prove it as a lemma. Yeah, I just didn't want to put it as a slide.
And the have from stuff is to do with the tactic language.
That's yeah. So it's actually just it's actually just the it's just part of a proof term. What it does is it really just puts it into the context. So it's so have is really implemented as kind of a lambda and then apply at the end.
Oh, I see.
Insert, yeah. And
The let really.
what?
It's a let really.
It is it's an opaque let. Well, we can talk about the difference afterwards, but you don't have you can't unfold the it just sort of puts the object in the context. We can talk about the difference.
What happens if you drop the from sorry? You just say have.
Oh, that's a syntax error. So the syntax is have. You can give it a name. You can have h colon the thing that you have, and then you have to give the proof justification.
It has to be a from.
That has to be a from. Yeah, that's the syntax.
And the if with colon. This was also interesting in your previous. If h colon then some position or what is it?
Yeah. So what was the question?
I mean, how does this?
The ifs.
No, the if
Oh,
it
there's
was in the previous one.
Let me get to the if later. I'll talk about the if later. Okay, good. That's another good thing to talk about. Actually, I told you, there's just a lot to tell you about, right? So yeah, so I'll come back to the if later. Type class inference, it's really built into the design of the system, from the start, from the beginning. It works well. Let me not talk about that now, because again, there are too many other things to talk about. And most of you are kind of familiar with type classes anyhow. Yeah, so let me skip that. We also, so I said that Lean has nice syntax. I mean, it sounds petty, but it's important, right? I mean, when you're spending a lot of time typing, you really care about the syntax. And so, we've done a lot of tinkering and fiddling to get the syntax really nice. And so we've got, in Lean 3, we've got a lot of nice gadgets. So let me just describe some of them. So we've got these anonymous constructors and anonymous projections. So for example, if you want to prove PNQ implies QNP, right, the canonical way to do it is you assume PNQ, so that's a lambda h, and then you take the right part, you take the left part, and then you put them together to get the proof of the conclusion. But you can also write the same proof as lambda h, and then the pointy brackets, h right, h left. And the idea is, you don't have to say and right h, because h is an and, Lean can infer that. And so, this h dot right means, we'll figure out that h is an and, look at the namespace and, find the right, the right projection, and use that. Similarly, and intro, you don't really have to specify that, remember the name and.intro, right? It knows that you're trying to prove an and, so it can infer that. So pointy brackets just say, find the relevant constructor and use it. So it's just kind of neat. So here's another example of how you might use it. So you can say, if you have the list function, you can map the square function on the numbers 0 to 9. But you can also write it this way. You can say, take the numbers from 0 to 9, and then apply the map function with this thing. And the $sign we're just using as in Haskell, or it's an ML. I guess an ML it's used. This is just application, but it's a nice way of doing application without having to remember to put a parenthesis at the end. Yeah, so there's that. There's a lot of nice notation for records. Records are just inductive types with one constructor, but there's nice notation for defining records and with all the projectors at the same time. You can give them default values. So up there, you define the structure color with 3 projections: red, green, and blue, all natural numbers. And you also assign your default values, saying that, look, if I don't specify, just take 0. So you have default values. What can you do? And you have different ways. You can write color.make to use the constructor, or you can use the curly brackets notation. Oh, there's also nice record update. You can say, make lavender, we'll take this record, hot pink, take all the values from there except change green to 20. So it's kind of convenient to use. Also, pattern matching. There are lots of gadgets to make pattern matching look nice. So we've already seen like the equation compiler. The first example is how you would prove if there is an x such that p of x and there is a y such that q of y, and there is an x and a y such that p of x and q of y. The first one is just the function compiler. But you don't have to do that at the top level. Anywhere in a term you can use a match construct. So the second one says, match h0 and h1 with those 2 things, and then use it. So you can sort of do cases with a match. You can also use a let notation. So there's sort of like a case destructing let. And you can even do it with with the lambda. You can say, assume this, but assume it as xpx, and assume it as y qy. So all of these basically compile to the same thing. They're all just different notations. But because casing and pattern matching is just so common, there's just sort of nice ways to do it in the system. Okay. I'll talk about, so if you don't know what a monad is, I won't tell you now, but if you do, it's a very powerful and useful programming construct, and the parser has special support for monadic notation. So you can write monadic programs, and it's really generic. There's sort of there's a monad type, and you declare a monadic type, and once you have a monad, you can just start using monadic notation. And so all the standard ones, the option or maybe monad, the list, what's this one called, the non-deterministic monad. So all the standard ones are used. We'll talk about the tactic state monad in just a little bit. But they're monad. So there's good monadic notation. Okay, so those are some tactic engines.
So is it type or a type class?
It is a type class. So it'll infer the monad. Okay, so moving towards the metaprogramming, before I tell you how to use Lean as a metaprogramming language, let's talk about Lean as a programming language. So as I said, there's a fastbytecode evaluator. It uses a stack-based virtual machine. You erase type information, propositional information, and just evaluate. Let's see. Again, as I said before, Lean knows what's computable and what's not. And if it's computable, you get the bytecode right away. You can execute it anytime. So we use, for performance, we use nats and ints natively. So we use the machine versions, for if they're small enough, and when they get too big, it switches to GMP. So you have to trust GMP if you're using the evaluation. By the way, we don't use the virtual machine for proofs at all. So this is not. This is just for evaluating code reasonably reliably. There's an efficient implementation of arrays. So it's a functional implementation of arrays that is smart enough to know when there's only one thing pointing to it and do destructive updates. So there are tricks to make arrays more efficient. And it's really fast. So I don't want to make any strong claims because I don't know. I know when Leo was first working on it, he would compare, he would do benchmarks against OCaml and Lean compared favorably. So I don't want to make any strong claims, but it's really it's a programming language. It works. So it's on the level of interpreted OCaml and interpreted Python. Oh, and the plan is ultimately to also be able to compile down to LLVM.
Is there, I mean, the list of one-heads, is there an IO one-head?
Is there?
An IO one-head?
Yes, there is.
So
It's also
you can communicate with.
Yes,
with
there
your
is an
program.
IO mode, and it's also, I'll get to it in a couple of slides. Yeah, so good. So yeah, so first of all, you can sort of do, all the things that you find in, an introduction to functional programming, right? So, all the usual things that you've seen in the first chapter. Here's how you write expressions and evaluate them. But look, there's an if. So along the lines that you mentioned. So if, so you can say if 2 is less than 7, then 9, else 12. So 2 less than 7 is a proposition. So what's going on is that the if takes a proposition as an argument, but it also has an implicit type class argument that the proposition has to be decidable. So when you write something like that, the elaborator, to make sense of it, has to be able to find a decision procedure for the less than. And then when the virtual machine evaluates it, it forgets the propositional information and it just uses your decision procedure. Okay, so you're basically, writing. So I mean, this is where the programming language mixes with the assertion language. You're adding assertions, but with the assertions you have an associated procedure. The evaluation uses the procedure you've associated. The assertions are the assertions that you think they are, and you have proofs. You have proofs that the decision procedure, decides the proposition. So it really is a very nice instrument. And you don't think about it. You just write if 2 is less than 7, and it does the right thing. But there's a lot going on there. You can also put a Boolean there and have the Boolean coerced, the proposition for which it's its own decision procedure. So it all works. You go back and forth between the Boolean and the decidable proposition world very, very smoothly, so that you really don't even have to think about it. So here's just an example of just a binomial function, just written as a program. Okay, and again, you can do generic programming. So here's just like, here's the insertion sort. How you do an insert and so on. But if you have any type and any relation, and as long as the relation is decidable. So, you can just sort of write your generic, ML functional programming insertion. And then you can just sort of evaluate it with the, less than or equal to on the natural numbers as the relation. And so it really is a programming language. And so here's your question. So, so how do you do I/O? Well, so the way they implemented it is, there's sort of this abstract algebraic structure. It's like an I/O thing. It has, a terminal and terminal calls and so on. Okay, so you write functions that assume that you're given some kind of, I/O object. And then when you want to run such a thing, well, you can actually write your own kind of I/O object, or you can just have the virtual machine just use the real one. So you basically have an interface to standard input and output and file input and file handles and open and close and so on. And it really works. A couple months ago, we decided that we should really have a package manager for Lean. So rather than have one big library, you want to have lots of different libraries and dependencies and so on. And so, Gabriel wrote a proposal for, having you have a configuration file that indicates the dependencies, and you can do things on GitHub, and they can recursively depend on other things. And then it came time to implement it. So a lot of systems will use a scripting language like Python or something like that. But that introduces a new dependency. You have to install Python and which version. But look, we have a programming language, right? So if you want a package manager for Lean, you just write it in Lean, and he did, and it works. It works just fine. So the point is, it really is just a programming language. Okay. So now the question is, a metaprogram. So by metaprogramming language, you want a programming language because dependent type theory is so fiddly and difficult to deal with, right? You want automation, you want help building terms. You want to have means to extend the functionality of your system. So, how do you go about doing that? And, people have done lots of different things. You can use the underlying implementation language. So in our case, you can write tactics and automation in C++. And other systems, ML, OCaml. Yeah, okay. So you want to, so for some purposes, that's what you want to do, but often you want to avoid it. You can write domain-specific tactic languages just for doing many kinds of tactics. You can also use reflection as Untact does. But the answer if we chose a Lean is just to go meta and just use the object language as its own program. I mean, you want a programming language, and I just told you that Leanitself is a perfectly good programming language. So we'll just use Lean as the metaprogramming language for Lean. Right? And it's just you can use, we know that you can use any language, as a meta language for any other language. Right? You can, use anything to write, control terms and anything else. So it's just kind of a joke that we're using Lean to build terms in Lean. But there are a lot of advantages to doing it that way. I mean, one is that once you've taught somebody how to use Lean, then they already know how to do metaprogramming because they already know how to use Lean. And so everything you develop in the library, all your list functions and all your everything you develop in the object language is available for metaprogramming. Moreover, all the things that you build into the editor and debugger and so on to handle the programming language works for metaprograms. And this is really important to me, that you can then develop your libraries. As you're building your libraries, you can prove theorems, and you can write automation to support those theorems. And that happens just in the same file. Right? So you can write programs and metaprograms in the same, and they look, well, so I'll sort of show you in a minute how they look. But yeah, so that's the idea. So here's how you do it. Here's the trick. Here's how it works. So what you do is you take Lean. So you add an extra constant called tactic state, and you define a type of expressions. I'll show you that in a minute. And you add a bunch of constants to the language that act on the state and expressions and do whatever they do. Okay. And the idea is, from the point of view of the formal framework, these are just declared constants. They're unaxiomatized. The system, the tactic state is just this thing. But when you give it to the virtual machine, when the virtual machine has to handle one of these functions, it says, oh, wait, I recognize that thing. I'm supposed to use this C++ internal. So you add hooks, right, from so basically, the constants you declare give you hooks to Lean internals. And so when you execute the virtual machine, it's running the internal C code. And we use a tactic monad in a moment to support an imperative style of writing tactics. And so the idea is you stepped outside the axiomatic framework. I mean, if you're calling these functions, again, you're not being formal anymore. Their behavior is not described in the system. So Lean forces you to mark the definitions as being meta. And meta definitions are a little bit looser. You can do arbitrary recursion in a meta definition. Okay, so they're a little bit looser, but otherwise they look just like ordinary definitions in Lean. Okay, so you just write things that use this extra stuff, this API. So here's just a simple example. So here's how, in fact, how the assumption tactic is implemented in Lean.
Sorry, question. What type does the type of expression have? Is it in the first universe or?
Yes. So it's type 0.
Is that true for tactic state as well? Is that
yeah, so pretty much, so you do get universe props, so most things are, so for most concrete things, we just put it in type 0. Yeah. Okay, so here's a procedure that, so what find does, it takes an expression and a list of expressions, and it looks for something in the list of expressions whose type is or unifies with the expression. So it's find that type, find something of that type in that list. Right? So here's how it goes. If you've got type E and the list is empty, you just failed. Okay, so you're returning something in the tactic monad. It's a stateful monad with a failure, so it's like an alternative monad. So if you're looking for something in the empty list, you fail. If you're looking for the type E in H, cons with H's, well, first you infer the type of H, put it in T. You try to unify E with T, right? And this might change the state. It might instantiate some metavariables. But if you succeed, you just return H. Okay, so the state has changed. You maybe instantiate some metavariables. and you return H, you've succeeded. Otherwise, if that fails, recursively, you call find on the remainder. So here's what the assumption tactic does. When it gets called, find me the local context, find me the type of the goal, search, call that routine to search in the context for something that unifies with the type of the goal. And if you find it, just apply it. And otherwise, just fail with an error message assumption tactic. So you define that, and then you use it. So here is just by assumption. So by says prove the goal using this tactic, and the tactic gets called. And the thing is, if you don't like that assumption tactic, you can write your own. You can change it, make it do something different, right? And you can do it, write above it, and then just use it. Write assumption, and then just use it. Okay, so yeah, so let me just say a little bit about. I'll go maybe for another 5 minutes, and then stop. Yeah, okay. So to make this practical, you start to realize that metaprogramming, you're dealing with syntax a lot. And so there's some basic syntactic objects. I mean, the main ones are their names. So these are like the identifiers, like variable names like x, but list.reverse. They're hierarchical, so list.reverse and so on. There are expressions. And then Lean has a notion of a pre-expression. A pre-expression really is just a variant of an expression. But the intention is that a pre-expression is kind of an expression that hasn't yet been elaborated. There are holes in it. It needs a little bit more processing. Let me just try to give you some examples. So first of all, internally, here's the expression type. And so you've got application in lambda, in pi. So that's familiar. You've got the sorts. You've got constants, and you've got this is a let definition. And then the first three it's confusing the kind of different kinds of variables. But so vars are bound variables, they're run indices. And lconsts are the local constants, they're variables in a context. So Lean uses a locally nameless approach. So when something is bound, it's a run index, and then when you open it, you have a local constant in your context. And then mvar are meta variables. So that's what your expressions are. And the idea is you have that, and you can do things by recursion on that. You can pattern match on expressions and so on. They're nice mechanisms to make this workable. For efficiency, there's another typo. But efficiency operations on expressions, the virtual machine actually uses the internal version of expressions. There are various ways to quote expressions. So for example, in the first one, it gives you a proof of true and true. And what do? You're saying take the expression and intro trivial, trivial, elaborate it. So turn that into an expression, and then apply it. Okay. And again, what you're really doing is, it's confusing. This meta stuff, meta is meta. It can be confusing, right? But what you're doing is, so the tactic is this independent thing. It's elaborated in its own context, and then you run it to construct, a proof of the theorem. Okay, so the idea is, any time in any expression, when Lean is elaborating any expression, you can insert the word by and then give it a tactic that's then executed to fill that part of the expression. So the backtick means elaborate when the tactic is defined, fill in all the information, and returns an expression, and then you're just applying the expression. Okay, so you can do it, in the by do, or you can separate it into two pieces. Foo is kind of a silly tactic; it does nothing but prove that theorem. But conceptually, that's what's happening. You have a tactic, and then you prove the theorem by just executing. But sometimes you can't elaborate right away. Sometimes you have information that isn't available until later. So, for example, to prove P implies P or false, well, you want to introduce the P, give it a name H, and then form the expression, or insert left H. So the %% E is an anti-quotation. And so what this does is the double backticks. What that does, it returns a pre-expression. It's an expression that's not elaborated, when the tactic is defined. It's just something waiting to be elaborated. And to expr, what that does is it elaborates it at compile time with the value of e inserted over there. Okay, so you can elaborate right away. Boy, a lot of typos. Okay, I'll fix that. So you can elaborate it right away, or you can defer it. That says elaborate later. Okay. And moreover, you can actually even, the more ticks the better, right? You can even defer a name resolution. So triple backtick means produce a pre-expression, but even names wait to resolve until the last minute. So for example, here you say intro H, and then convert or in left H. So here I'm not using an anti-quotation, I'm just saying use that. The idea is that argument H doesn't even exist until you run the tactic and introduce it. So that says, at the time that the tactic is run, take that pre-expression, elaborate it in the context at that time, turn it into expression, and then apply it. And the crazy thing about that is, so those of you who are used to writing tactic proofs in Coq, for example, you're used to writing things like that, right? That kind of blur this distinction between what's a name, and you have the illusion that H really is something, in the global world. But so in Lean, this basically compiles down to that. So this is the interact, and so the metaprogramming gives you very fine control and very much awareness of what names are and what expressions are and when they're resolved and when they're elaborated. And then for ordinary users, the interactive tactic mode kind of blurs all those distinctions. But this very directly compiles down to that. Let's see. Okay, so let me just say, so here's how we do metaprogramming. We extend the object language with a type that reflects an internal tactic state as well as operation. So this is just summarizing what I just told you. You reflect the syntax, so you have mechanisms to handle quotation and pattern matching and so on. We use a tactic monad to write programs. We also have ways of declaring attributes. We have an attribute manager. It's a really powerful API. And so let me just mention that most of Lean's tactic framework is currently implemented in Lean. So all the usual basic, the core basic tactics are implemented in C++. Large-scale automation that has to be performant will be in C++. But once you have that, lots of basic things are implemented in Lean, including a full-blown superposition theorem prover has been implemented for Lean in Lean. It's not very optimized. It's not very fast, but as proof of concept, try that with LTAC. It's kind of remarkable that you can do that. Let me jump to conclusions. So we're off to a good start. We have a good logical framework. We have efficient infrastructure, nice syntax, a powerful elaborator, good basis for user interaction. Automation is starting to show signs of life. But we're really excited also about the metaprogramming facilities that I've just described. That you can develop theories and procedures to work with them at the same time. Or even if you want to use Lean for back-end automation, you have very powerful ways of sort of developing customized automation to do whatever you want it to do. We see so the system, things are moving along nicely. There's still a lot to do. And so if you're young and energetic and looking for, you've got all this pent-up energy and you really want to do something that will change the world, this is a good project to get involved with. These slides are already on my webpage. I'll fix the typos. So on the Lean main webpage, you'll find documentation papers. And in particular, we've got a paper on the metaprogramming language that has just been accepted to ICFP. And so that's up there. You might want to take a look at it. Okay, thanks very much.
I'm told that any theorem prover worth its salt has to have several subtle ways of proving true equals false. So does Lean have
As far as I know, it doesn't.
Surely with metaprogramming you must be able to.
Well, I'm sure. Yeah.
I mean, when I say prove true equals false, I don't
so,
mean as it were in the logical core of Lean, but
Yeah, so
But
the
apparently
tactics,
the user ends up with a
the
theory.
tactic language, metaprogramming can be fallible, right? So you can write programs that fail. You can really get in and mess around with expressions, and you can screw up. You can produce expressions that don't type check. But anything that's ever added to the environment is checked by the kernel. So you're not threatening soundness in any way. So you do have a flexible metaprogramming language, but everything you do is checked at the end.
I'm prepared to believe that your kernel is probably.
Yeah, and well, so again, the kernel, because it's so simple, the kernel is fairly small, and as I said, people have one bit of evidence that the kernel is manageable is that people have been able to write. So there are independent reference checkers in there's one in Haskell and there's one in Scala. So it's at least simple enough so that somebody else can write a checker.
Can you draw pictures, Emily?
Can you draw a picture? Not yet. But people are excited about it. People are excited about VS Code that you can. I mean, VS Code. I mean, people really like.
You don't mean ASCII art.
You can do.
Yes,
No, people are really excited about the editor in VS Code. You can put in HTML. You can put in LaTeX. Not yet. But
So in the future we will be able to write our scientific articles directly in Lean.
yeah, that would be nice.
Lean has a pretty excellent Emacs page. Who was responsible for that?
So I mean, a lot of people. Sin Ho Kong wrote the first one. Gabriel Ebner, Sebastian Ulrich have done a lot of work on it. So those are the main three. Jared Roche implemented the first VS Code, and people were also working on that, including Sebastian and Gabriel. Yeah, and of course Leo. I mean, they're all working very tightly with Leo, coordinating the back end.
So all these cool metaprogramming sort of features, these are all in Lean's 3,
Yeah.
which is not yet the one
It's
on
not-
the
That's right. Yeah.
Is the hot support expected to be pulled forward in Lean 3?
It's
or
not
is
on the
that-
horizon yet. We can talk about it afterwards, and the reasons for the split and so on. I mean, the short, I mean, there's nothing nefarious about the reason for the split. It was, I mean, just a matter of Leo just being over constrained and so on. So we can talk about the stumbling blocks and the difficulties of, and the benefits, and so that we can talk about it offline. So there's no, it would be nice to have, and nobody's ruled it out. But
So
there's
there's
no
theoretical
concrete,
issues
there's
with
no
it, it's
concrete
just a matter of
projected, no
finding
concrete plans.
some-
Yeah. So again, if it'll take somebody maybe young enough and energetic enough and enthusiastic.
What's the status of documentation? Boring but very important thing.
I'm sorry, yeah, so with the tutorial, I mean, I'm feeling guilty, I should have been working on it this week. Making these slides. No, there's online with the tutorial system, there's something called, the main one's called Theorem Proving in Lean. We have another one called Programming in Lean, and another one called Introduction to Lean. There are these, I mean, there are a couple hundred pages of documentation.
Yes, that's not quite what I meant though, because that's like your view of what I should know.
Yeah.
But I meant more like,
The reference.
we've got a list of the keywords.
Yeah, so that's
kind
another,
of
we're getting a
boring
lot
crap,
of
but
we should
it's
have a
actually-
reference manual. Yeah, so
You never know
Jared
what
got
the
all
user wants to
excited,
know.
set up the infrastructure for a reference manual, and then didn't really do much. So, yeah, we know, it's on a to-do list, it's on a to-do list. Part of it, one of the reasons why is that it's even fundamental things are still evolving and changing in keywords and syntax. We're still fiddling and tinkering. But yeah, we know that we need a reference.
And unfortunately, it doesn't sort of enhance a PhD student's career to spend half his life doing documentation.
Yeah, but working on the other bits of documentation, I mean, it is kind of, it's such a fun system to talk about. It is nice to document.
So how do you see this develop? Will all the other systems steal all the cool features from Lean, or will Lean just push all the old systems away?
Well, I mean, again, we're not.
Should we have translation between systems?
Yeah, so
Should Lean be a backend?
again, the hope is that Lean can be used as a backend system to other kinds of automation. Yeah, I mean, we're not trying to crowd anybody out, and yeah, no, we're just trying to design a good. Yeah, I think so. So one idea is to have Lean, be usable as backend automation to other things.
Is there any hope to compile inductive recursive definition on inductive?
Yeah, there are no plans. I mean, people keep asking about inductive recursive, inductive. It's not on the high priority list. Again, if somebody young enough and energetic enough and enthusiastic enough to get into Leaninternals, but there are no plans right now to do inductive. I mean, I guess in principle, which is the one inductive should be compilable down to. Do you have any sense of whether that's even remotely feasible? Yeah. Okay.
Yes, so
Sounds like
large
a
inductive
return
recursion is a
to
proper
the
extension that will allow you to prove consistency of the system. So that would require kernel extension.
Yes.
But small,
Well,
small
would
ones
kernel
should be
extension,
compilable.
could you get it by just declaring an extra act? Would it require an actual kernel extension?
If you wanted to compute, probably.
But anyhow, it's not, there are no plans right now.
Is there a sort of, can I roll my own syntax?
Yeah, so, you're getting me with the last few slides. So once you have a programming language around, you can do all kinds of crazy things. So, I mean, you can use it to write your own tactics and automation. The interactive tactic state, that's purely configurable. You can have your own state and tell the editor what to display at each line and have your own syntax and so on. So you can extend the tactic state and customize that. The debugger is fully customizable. You can write little hooks. You can say, I want you to give me a callback, when this function is called with these arguments and so on. Sebastian has been working on parser extensions. So when the parser hits something, it then calls your tactic, and then you tell it how to parse. So once you have a programming language kind of built in, you can really make everything configurable. Yeah, I mean, years ago with John Lamont and Dean, so we designed a formal system for Euclid for doing proofs like you would see in Euclid elements. And my dream one day is to be able to do that in Lean, be able to write, like P be a point, like P and Q be points, like all people want, and just do that purely in Lean. So yeah, so I think it is good. So I think it's a good place to embed other logics and experiment with them. I mean, people haven't done that yet, but I think it should be flexible enough to support that, and I'd like to see people try that as well. Okay, I've gone way